Hi, we are going to simulate the buck converter we have designed, taking into account the components we have selected. So our target is to see if we identify any difference with respect to the ideal simulation. So here we can see the schematic of our simulation circuit. We have seen all parts of this circuit in different videos. So here we have the MOSFET, considering the specific device we have selected. Here you can see the control of that MOSFET with the small modification that we introduce in order to properly control the device. Here you can see the diode with the specific model. Here you can see how we model a real inductor, in our case with a resistor in series with the inductance, and the model for the capacitor, which is the ideal one. Here we have the simulation configuration. Here we have the library, or the instruction for including the library of the MOSFET, and here we have the definition of two parameters we use, the duty cycle and the switching frequency. As you can see, here we have a modification with respect to the ideal simulation, because the theoretical duty cycle is 0.275, but here I have modified the duty cycle. Now is 0.296, so I have increased a little bit the duty cycle value. And why I modify this? So the answer is related to the output voltage. Here we can see the output voltage evaluated at for two different values of duty cycle. In red, you have the output voltage when the duty cycle is the theoretical one. And in green, you can see the output voltage when the duty cycle is the new value I have selected. So, as you can see, when the duty cycle is the theoretical one, the output voltage is lower than our target, which is 3.3 volts. So I have to increase the duty cycle in order to reach the target. Okay, so if you check it in the simulation, you will see that the duty cycle that allows us to obtain the desired output voltage is that value. Why we have to do this simulation? Why we have this change with respect to the ideal simulation? Well, the answer is that in this case we have the real models of the components. Okay, those models include the parasitic elements, the non-ideal operation of those components. So as a consequence, we have that. Okay, we have this small difference, and we have to increase a little bit the duty cycle. Okay, so what we are going to do now is to check different waveforms, the same waveforms that we studied for the ideal simulation, and we will try to identify if we see any difference with respect to those results. So for instance, we can check the output voltage in detail. Okay, note that here we have 3.31 volts and here we have 3.29 volts. Okay, so if we see that in detail, we can confirm that the output voltage, the average value, is the one that we want, and the peak-to-peak output voltage ripple is not the theoretical one, but is really close to that value. It's not the theoretical one because, well, the inductance is not the same as we consider in the theoretical analysis, the capacitance is not the same, and moreover, we have modified a little bit the duty cycle. So, well, this peak-to-peak output voltage ripple is in the range of tens of millivolts. Okay, I think that it is around 16 millivolts, 17, close to that value. Okay, let's explore other waveforms. In this case, we see the current through the inductor in green and the current through the load, the output current, in red. So, well, it seems that the waveforms are close to the ideal waveforms, because as we can see, in state number 1 the inductor current rises, and in state number 2 the inductor current falls. And moreover, if you check the screenshot, the average current through the inductor is the output current, so it's the same result that we obtained with the ideal simulation. What happens if you check the waveforms in detail? You will see that there are small differences. For instance, if you check the peak-to-peak current ripple in the inductor, you will see that it's not exactly the same value due to the reasons that we have explained before. But in general, until this point, the conclusion is that the results are very similar. Well, let's see another couple of waveforms. In this case, we see here the control voltage, and here we check the voltage across the MOSFET. Okay, the target is to see if we are controlling properly the MOSFET with the modification that we perform in the control signal. So as you can see in the control signal, here we have, let me change the color. Here we have 12 volts in order to turn on the MOSFET, and here we have 0 volts in order to turn off the device. When the device is on, we have a short circuit. Well, in the reality, in this model, what we have when in the MOSFET when we turn on the device is the on resistance. So if you check this value, that voltage is not 0, okay? It's a small voltage, a small positive voltage, but it's not 0. Then when the MOSFET is off, what we have is an open circuit like this one. So here we see the input voltage. Okay, well, the waveforms are close to the ones that we obtained with the ideal simulation. Now let's see what happens if we keep the bottom waveform. So here we also have the voltage across the MOSFET, and here we have the current through the MOSFET measured in that way. So what we see in the current waveform is here the current through the MOSFET is the inductor current, here the current through the MOSFET is 0. But as you can see here, we see an important difference with respect to the ideal simulation. When we turn on the MOSFET, we have this peak. So it could be a problem, and it will lead to power losses. So this is something that we will explain in detail in another video, but the conclusion here is that we have identified a difference with respect to the ideal simulation. Let's try to do the same with the diode. So I will draw in the top waveform, I will draw the current through the diode, and in the bottom waveform I will draw the voltage across the diode. So if you check the current through the diode, you will see that here the current is 0 because the diode is off. When the diode is on, it drives the inductor current, and here when we turn off the diode, we see a negative current peak. That peak is the same peak that we saw in the current through the MOSFET when we turn on the device, because this is the same instant. At this point, the MOSFET is turned on and the diode stops conducting current. So this is a effect that is called reverse recovery, and we will talk about that in future videos. So, well, here we see another difference with respect to the ideal simulation. And when we check the voltage across the diode, what we see is when the diode is off, okay, when we have an open circuit, it blocks the input voltage, as in the case of the ideal simulation. And here, when the diode is on, we don't have a short circuit, okay? Our diode, when it's on, has a forward voltage drop. In the case of the Schottky diode we have selected, this is 0.5 volts. Okay, so as a consequence, if you check this value, this is not 0. Okay, what we have is minus 0.5, sorry, 0.5 volts. And well, this is, it seems that it's not very important, but in practice, when we evaluate efficiency and power losses, it will be one of the most important problems we will find. Okay? So finally, I want to evaluate output power, input power, and efficiency. So here we have the output power is constant because we have a constant output voltage and a resistive load. And here we have the input power. We call, and as in the case of the ideal simulation, is a pulse waveform, okay? Because here we turn on the device, here we turn on the MOSFET, and here we don't have current because the MOSFET is off. Well, as you can see here, we can see the current, well, in this case, the power peak that we have identified in previous waveforms. So that effect also appears here. And well, if you go or if you try to evaluate the efficiency, you know that we need average output power, average input power. We can do that very quickly with LTspice. We use the average function of LTspice, and you will see that the average output power is 50 watts, as we expect. Okay, but when we evaluate the average input power, you can check that the value is 56.6 watts. So our power losses are 6.6 watts. It means that our load consumes 50 watts. So let's say that we properly supply our load, but we extract from the input 56.6 watts. So we have an extra power consumption that is dissipated in our power converter. As a result, if you evaluate efficiency as the ratio between output power and input power, you will see that the efficiency is 88%. So it's not 100% as in the case of the ideal analysis or as in the case of the ideal simulation that we have performed in previous videos. So our target, or let's say that the conclusion here from this video is that there are small differences between the simulation when we consider the manufactured models and the simulation when we consider ideal models. Our target for next videos is to analyze one by one each difference in order to identify where we have the extra power consumption that we see here. In other words, we will identify where we have the power losses. Okay, so see you